Good morning. My name is Miguel Liroz. I'm a PhD student at the Zenit team at Montpellier. And today I'm presenting the work which is entitled MapReduce, Minimizing Data Transfer Between Mappers and Reducers in MapReduce. So this is the structure of the presentation. First, I will give an overview of MapReduce, and in particular, we focus on the shuffle phase. Then I will motivate our approach. In particular, I will point out which are the limitations of the shuffle phase, and I will define the problems that we want to solve. And after, I will present our approach, which we call MapReduce. And finally, we are going to present some experiments that we have run and the conclusions. So first, let's do the review of MapReduce. So as I guess many of you know, MapReduce is both a programming model and a framework that was introduced by Google that was intended for high parallel processing of large-scale datasets. In particular, it was aimed at the parallelization of some problems like PageRank algorithm or the generation of inverted indexes. And it normally or typically is used in combination with other Google services like GFS, the file system, Bigtable, or Social. So the main features of MapReduce is that it provides automatic parallelization and distribution and fault tolerance in a transparent way to the user. There are several implementations of MapReduce, and some of them open source, and the most popular one is Hadoop, and is the one that we have used. So in MapReduce, the data consists of key value pairs that we also call tuples. And the users have to provide two functions. The first function is called map, and it reads input key values and produces a list of intermediate key value pairs. And there is the reduce function, which reads for each key, intermediate key, all the values that have been produced in the map phase, and produce a list of output key value pairs. So this is a typical example of MapReduce. This is the problem of word count and how it's implemented in MapReduce. So just in the map phase, just we read each line of the file. So we are given the key is the offset of the line, and the value is the content of the line. So for each word in the line, we emit just one, because we have found the word once. And in the reduce, we will receive for each of the words as many ones as words we have, as times that we have found this word. So we just have to sum up to add all these values and emit the final count. So this is a schema of the execution of a job in MapReduce. So normally, MapReduce is used over a file system. In this case, I use HDFS, which is equivalent to GFS, the Google File System. In HDFS, the files are partitioned in several chunks. And these chunks are used by the map function to divide the input of the job. So each map task receives a part of the input, which is called a split. So there are several map tasks which execute in parallel, which is called the map phase. And then there is an intermediate phase, which is the shuffle, which we'll see later, and which it is in charge of grouping all the values for the same key. And finally, all the reduce tasks will receive the values of the keys and apply the function provided by the user and generate the output. So we focus on the shuffle phase. So we have divided the processing of the shuffle phase in two parts. So in the first part, which is carried out in the workers that run the map task, the output of the map task is partitioned into as many fragments as reduce task. So by default, there is a partitioning function, which by default is just a hash on the key module, the number of reduce tasks. And then the tuples within a partition and sort, and optionally we can apply a function for optimization which is called a combiner. Then in the reduce part of the shuffle, each of the reduce tasks fetch the output of the map task and then matches the lists and provides groups the elements with the same key and send them to the reduce function provided by the user. So now we have seen how more or less how MapReduce work. We are point out to the limitation and motivate our work. So one of the limitations of MapReduce is that in the shuffle phase, we may have to perform a lot of data transfer through the network in order to transfer the information from the map task to the reduce task. And this transfer is done at the same time by all the computers, so they are competing for bandwidth, and as a result, the execution time of the job may suffer some overhead. So in an ideal case, there will be no data transfer because the values of for the same intermediate key will be produced in the same node, and we will schedule a reduce task that is in charge for that in the same node as well. So here I show you what I was saying with a figure. So in a normal case, well, in the left part we represent the input, and the color represents the intermediate key produced by each of the input tuples. So in the normal case, these tuples are distributed over the output of all the map tasks. So in the shuffle phase, we have to perform a lot of transfers. If we come up with a situation where the intermediate keys are collocated in the same nodes, then we can avoid those transfers. So this is the idea of our solution. So in order to know how many transfers are going to be performed in the shuffle phase, there are three mechanisms in MapReduce that are involved. First, how the data is partitioned in the input splits, which after will generate the intermediate keys. Then, which is the partitioning function, which will assign intermediate keys to reduce tasks. And finally, how these reduced tasks are going to be scheduled to the workers that execute those tasks. So in the related work, there have been some analysis of how much is the overhead of data transfer in the shuffle phase. There have been some works in simulations over different network topologies and in experimentation of the real clusters that have proved that it may pose a significant overhead to MapReduce jobs. So there has been some works we have tried to optimize this phase by reducing the number of transfer through the network. So in the first approach, what they do is they try to schedule reduced tasks in the nodes that will minimize data transfers. The second work that here I present is more fine-grained in the sense that it does the scheduling at key level, not at scheduling level. So intermediate keys are assigned dynamically at reduced time to the reduced tasks. And then, of course, the reduced tasks are scheduled in the nodes to minimize data transfers. So these works focus on the two second and third mechanisms that I mentioned before. So the problem is that if the intermediate values are distributed over all the map tasks, this approach cannot benefit from that, and the total amount of data that is transferred is not minimized. So we are focused on this part of the problem. So in our problem, we define the input as files which are composed of tuples, which are key value pairs. And we have a workload, which the workload actually is a set of MapReduce jobs. For us, we don't know anything about the schema. We don't know anything about the MapReduce jobs. So for us, the map function is a black box. So we want to come up with a general solution that minimizes the amount of data transferred through the network, by using the data partitioning in the input. So we call this approach MRPart. So this is the main idea. I already talked about it, but we want to pass from this situation in which the intermediate keys are produced in all the maps to this situation where we group the intermediate keys that are produced by the map, and then we can profit from the other mechanisms that have been proposed. So our approach consists of three main phases. So we have a phase which we call monitoring, in which the MapReduce jobs are executed, and then we inject a monitoring component which detects the relationships between input tuples and intermediate keys. So these produce some metadata. With this metadata, we generate a workload model. We model the workload through a graph, because the graph represents relationship between elements. And then we use graph partitioning algorithms, as there are several libraries that we can use for that. And with the result of this partitioning, we repartition the input. And with the new input, by applying a locality-aware scheduling algorithm as the approaches that I mentioned before, we can minimize the data that is transferred. So I will go in more detail over these phases. So for the workload information, we want to capture the relationship between tuples in a file and the intermediate keys. But this is not straightforward, as there is no semantics over the key or the combination of key values. So the only way we can identify input tuples is by knowing in which split they have been generated and in which order. So with this, we generate the tuple IDs. So each own map task generates its own metadata, and we want to repartition as this data is combined in order to generate the workload model. So the monitoring component that we have designed is very simple. Each time an intermediate key is produced, this data is written. So just we add a line there in order to generate that the metadata that we need. With that, we don't have to generate for each element the file and the offset, because it's the same for all the split. So we generate a metadata files, which for each intermediate key we have the input tuples that have been that produce it. When we have all the information and we trigger the repartitioning, we generate a graph with this information. We are using hypergraphs because they are more efficient in terms of representing relationship between a lot of tuples. The difference between hypergraphs and graphs is that in hypergraphs, the edges can connect more than one vertex at the same time. So for instance, here we have the same line of the metadata in which key 1 has been produced by tuples 1, 2, 3, and 4. So this will add an edge will connect the four tuples. So we can generate the graph incrementally, and then when we have all the information, we have the graph we represent as a workload. And from this graph, we can apply graph partitioning algorithm. We can use some of the libraries that exist. And then with the result of this repartitioning, we can reorganize the tuples of the input of our MapReduce jobs and repartition the data. So one possible challenge is to have big graphs, but we provide some solutions for this problem, such as leveraging on the fact that we are using a parallel infrastructure and provide and use parallel versions of the graph partitioning algorithms, and also coalescing equivalent tuples in order to minimize the amount of vertices that are present in the graph. Finally, we have to change the scheduling mechanism of MapReduce. So something which we call reduced locality-aware scheduling, and what we do is we use the approach that was given in this work, in which intermediate keys are assigned to the reduced task that is going to be scheduled in the node which produce this key with higher frequency. So now I will show some results from our experimental evaluation. So we have implemented the MRPart in Hadoop, and we have tested in Grid 5000 platform. We have compared native Hadoop, Hadoop with the modified reduced locality-aware scheduling, and our approach. And we have used TPCH, in particular the peak implementation of TPCH, in which queries are written in a language which is on top of MapReduce. We measure the amount of transfer data and the response time of our jobs, and we vary some parameters. So in this graph, we saw the results for some different types of queries. So we compare the red bars are the native Hadoop. The green bars are Hadoop with the modified reduced scaling, and the blue one is MRPart. So as we claimed before, if we don't have a proper distribution of intermediate keys, even if we have a different reduced scheduling algorithm, we cannot gain. On the other hand, if we repartition the data, we can reduce significantly the amount of data that is transferred through the network. This is the same metric, but for a decreasing size of the cluster and an increasing size. And we see that our approach stays. This is the percentage of data. So actually, more data is transferred, but the percentage of total data that is transferred in the shuffle phase is local. And finally, we have measured the response time for different bandwidths at different queries. And our approach is not affected so much by the bandwidth. And this is the result of reduced shuffle time. In our approach, the shuffle time remains constant, while in MapReduce, normal MapReduce, the shuffle time increases. So to conclude, we have presented a new approach for minimizing data transfer in MapReduce. It's a general approach which is based on monitoring map tasks and characterizing the workload through a graph. Then we apply a repartition which is based on a graph partitioning algorithm. And then by using locality-aware scheduling, we can reduce the amount of data that is transferred to the network. We have performed some evaluation and saw this significant transfer in reduction in transfer data and the impact that it has on response time. We think that this fits very well to community and federated clouds where there are some links that are shared by many users, and the bandwidth is a scarce resource. So thank you, and if you have any questions.
Okay. So thanks for this very interesting talk. So I have a question. So you analyze, your first step is to analyze the map task and the graph, which is arising in this way. But this depends very much on how you partition the data, how do you store the data in the first place. So have you made any thought about because maybe based on the design of how you store the data, you design your map tasks, or maybe you use a different storage scheme or a different map scheme if you have a different storage scheme. I can give you.
So actually, when we model the workload, we don't know. Our model is independent of how data is stored at the first place, because what we have is relation between tuples and intermediate keys. So as I said, there is a challenge because we cannot identify a tuple by the key, but we have the position we can retrieve because we have the same input, so we can retrieve the same tuple with this mechanism. I don't know exactly what do you refer with different schemas of our approach uses the the typical situation in MapReduce in which the input is stored in HDFS, in files which are then partitioned in chunks. But these chunks, the order in which these chunks are processed, it doesn't matter. So I don't know if I'm answering.
So people often think, how do they put the data to the storage?
Sorry?
So you don't assume anything about...
No, we don't assume anything. If the user has a prior knowledge, maybe he can do better than our approach, because our approach is blind in the sense that it doesn't have any knowledge about the semantics or the schema. So of course, if you have a good knowledge of maybe you can have a better partition proposed by yourself, but our idea is to do it automatically.
Yeah, so if I understand well, you analyze the intermediate keys produced by a MapReduce job, and you group the input on the intermediate keys. Is it right?
Sorry, can you repeat?
So you analyze the intermediate keys produced by the map phase, and you group the input on these keys. Is it right?
Yeah.
So it depends on the job. So if you have several jobs, how can you have a global input which is satisfying?
In the graph is generated from several jobs. So in the jobs, if there are some tuples that normally in different jobs are grouped together, there would be more edges, or the weight of the edges will be higher. So the graph partitioning algorithm would place those elements in the same partitions. Of course, if you have many different jobs with contradicting intermediate keys, then the approach is limited. It wouldn't work if each job does a different way and you have a lot of jobs.
It's just a question about the performance when you are partitioning the data. So how long it takes to partition the data?
We have our approach now is sequential, and it takes more or less the same time as a MapReduce job. The same amount as a MapReduce job, but we plan to do it in parallel, do all the process in parallel. So actually, what is the overhead is the I/O related to rewrite the whole file. So this is the limitation.
So I think, okay, I have a little question about, there is initial investment to make the graph partitioning, to scan a little. Do you think how much processing you have to do to amortize this initial investment? Because if you run it like that, okay, you will have transfer during the shuffle, but instead of that, you will invest more, you will prepare more, the loading will be a bit more complex. So if you make a complete comparison, including the loading time, do you think how much processing you have to do just to amortize this initial investment?
Well, that will depend on the. We don't have this calculation. It will depend on the workload, but as I said, the execution time of the repartition is more or less the one of a MapReduce job. So once you have a few MapReduce jobs that can take benefit from this approach, then you will amortize the cost of the repartitioning. So if you're going to do just one time processing of the file, it is not worth the whole repartitioning. If you are going to do several jobs over the same files, then it's we don't have a cost model about that.
Okay. I just have one quick question. What about the maintenance cost? I mean that if we have new queries in the workload, do we need to compute the repartition of the data from scratch, or there is a way to do it incrementally?
Yeah, for the moment it's not incremental. It will be an interesting thing to explore, how to make it incremental and reduce the repartition in that way. But in our current work, it doesn't have this feature.
Okay, thank you. So let's thank the speaker again.